I know.
Welcome back to Medicinal Mass Debates. I am Demon Stride, and today we have got SeanG and Brian Flat Earth Tests doing a debate about Flat Earth. Welcome, guys. Go ahead and introduce yourselves.
You go ahead, Sean.
What up, SeanG, ex-Flat Earther. About it. It's pretty short and simple.
Did you say Sean G. Flat Earther?
Ex-Flat Earther.
Ex Flat Earther. Okay, I'm Brian Leake, FE Test. Subscribe if you want to see more of my content. It's Flat Earth Test on YouTube, and I've got over 200 videos. And that's about it. I'm an ex-Globe Earther.
All right. Well, thank you for showing up today. And we're going to start off the debate with Brian's presentation here. It's going to be a mixture of two videos. So let's get right into that.
So Ruib's talking about celestial navigation and distances. Let's check the directions. This is from North Florida to, I think, Sudan, near the equator in Africa. So it looks like we have to travel north. That's weird. So I'm around 30 degrees north, and to get by the equator, I have to travel north to go south. That's weird. Let's check it a little bit closer to the equator. So still have to travel north, maybe even a little further north. That too, that strikes me as a little weird that I have to go north to get south on their globe. I mean, that probably works on the AE map, but so let's check it south around 25 degrees. Well, that's weird. We don't have to go south in the southern hemisphere like we had to go north in the northern hemisphere. So let's go closer to the equator and check it out. Nope, still not going south in the southern hemisphere, but having to go north in the northern hemisphere. So that's just weird. Let's check these distances. So they say that 69 miles per degree doesn't work on a flat plane. So let's just test it. So 69.1 miles, and we'll put in for 1 degree change. So we'll put in 89 degrees in the triangle calculator for a flat plane. And what do you know? We get 3958.7, the exact globe radius. So if you're wondering where they got that from, where they even got that radius from, there you have it right there, doing flat plane trigonometry. And they just moved it to the center of their Earth. But let's see how that works on a flat plane. So let's check it. So let's check 138.2 miles and see if we get the 2 degrees. Let's check it because that's weird. They look like they hijacked the radius to me. So I put in 3958 for our height to Polaris because that's what we get when we triangulate on a flat plane. And for distance, I put 138.2 degrees. Let's see what that comes out to in the triangle calculator. What do you know? 88 degrees on the dot. That too is weird. So 138 miles we traveled, and it's 69 miles per degree is working just fine. So let's do 207.5. That's should come out to 3 degrees or 87. There it is, 87.006. But still immeasurable basically. So let's check, let's move up a little further. Let's go and let's do 691. That should give us 10 degrees or 80 degrees. And surely it does, 80.0 degrees. So seems to work pretty good on a flat Earth because we've traveled 690 miles and it's still working just fine. So let's do 15 degrees. That's 1,036.5 miles. And we put in 1,036.5 miles. Let's see if what we get in 75 degrees. What do you know? Coincidence? So let's try 20 degrees. Let's try 69.1 times 20. That's 1,382. So we're going to put that in the triangle calculator. We put in 1,382 382, and calculate, and 20 degrees. Must be a coincidence. So it's not until you go 1,500 miles before you're off by 1 full degree, and that's a long way. It's a little under 1,500 miles. So 20 degrees is 1,380.2 miles on a plane. So let's see what that comes out to. So if we're driving 70 miles per hour, so let's say 20-degree angle to a star, or, well, 70 degrees. That would 70 miles per hour. That's 2 10-hour days of driving nonstop. That's a long way. Let's see how long it would take to check that in a boat. Going 10 miles per hour, we'd have to travel for almost 6 days. So these distances that work so perfect on a globe they're uncheckable. They're untestable. Them are some long distances. But so I want to talk about the eclipse. This was the moon when it was about just a little crescent, almost fully eclipsed, but not quite. You see the sky's dark, and here's the sky's. This is the moon. This is looking west, and it's still dark. It looks a little bit brighter. The sun's starting to come up a little bit. It's probably not quite above the horizon though, and the facing west is still dark. But I show a sequence because I finally wait and until the last minute before the moon disappeared, and I film it and I catch the sun poking its head up above the clouds. But by that time, the moon side of the sky was daylit also. So check out the video. This is leading up to the video. This is the Selenium eclipse recorded from Jacksonville, Florida on November 8, 2022. The sun and moon are both above the horizon, and it is said to be the Earth's shadow casted onto the moon. I'm not so sure. You be the judge. The sun is about 2 degrees above the horizon. The moon is probably about 15 degrees above the horizon. And I'm about 30, probably 30 feet above sea level. So you tell me. And for any naysayers, I do realize you can't see the sun very good because it's so washed out. But you've seen how high the moon was above the horizon. So had it not faded out, I could have easily got it 5 degrees lower, which puts the sun 5 degrees higher. But I probably could have got it more like about 10 degrees lower. But still, I don't see how this works on a ball. Now, last but not least, I wanted to talk about refraction and the globe model refraction. This is a tank full of sugar water. Their only demonstration, and their demonstration proves a flat Earth. Look, we have direct line of sight. See that black line at the bottom of the city? That represents line of sight. And look at the lower you go, the more the bottom of the city skyline appears to vanish. It's bottom up obstruction with direct line of sight. So their their demonstrations literally backfire on them. So their only demonstration of refraction on a globe literally helps prove the flat Earth. So I want to welcome Ruhif to the flat Earth. There you have it right there. This is what refraction does. Y'all say y'all proved it. It the light bends down toward the denser medium, and well, okay. Well, there's what you get. You get half of the city missing with the light refracting downward. So, so welcome to Flat Earth, Ruhif. There's your evidence from Mick West. Um, you say you prove that the light does what it does, and well, there's the result. Bottom up obstruction. So I don't know what else to say. Let's get on with it.
Okay, and I have one more video. We're gonna look at chart. Oh, hold on. No Jimmy Kimmel. Okay, let me present the second one. Okay. And is this about where you said to line it up? I think you're muted right now. If you want me to back it up a little bit or pull it
started at
forward,
exactly
just let me know.
exactly 10 minutes.
Okay. All right.
From the top of the hill, I surveyed 9 locations along the aqueduct. I looked at the 7.5 degrees, saw a nice spread in angles. But the results were simply disturbing. The measured height along the aqueduct seemed to match the curvature of the Earth, but with a slightly steeper curvature, which makes sense because water has to flow downhill. But I had to replicate this because I couldn't believe my eyes, so I went back another day. This was an even better data set, very smooth. I was very impressed. It was a clear day, and I thought, this is it. I have to find out what that slope is. So I went to the internet. A quick Google search revealed that the slope of the aqueduct is on average 3 inches per mile. I decided to measure the water level in the aqueduct and walk downstream. I move it so the water moves a little bit. See that? Like waves there. There you go. 7 feet and 2 inches. They round off. So the level was about 7.5. So I thought, okay, maybe it's sort of going down. Okay, so we're by the pump house now. Here's the pump house, right? And yeah, we were, boom. This was the most distant point. And I used to aim around here. Gosh, the sun is shining. There we go. Right there. See that? I'm moving in the water. There we go. About 6 feet. Right on the curvature. See that? About 6 feet. The water level has come up, folks. Case number 1. You win. Unbelievable. A foot and 2 or 3 inches from over there. Yeah, very, very interesting. This the cement was, surveyed, laid out to follow the curvature of the Earth, and the water doesn't care about that. The water is like, you can do whatever you want. There you have it, folks. This is incredible, just incredible. The Earth is truly flat. Unbelievable. But yet there is an optical distortion, right? Light bends up because there's a gradient. Temperatures are warm across the surface. Exciting times, folks. The Earth is truly flat. You can bank on that. It looks flat at steeper angles, but at shallow angles, not. And they chose to measure the radius of the Earth at shallow angles. Bad scientists, bad. That's what happens.
So the gate is open 2.2.
Yeah.
2.2. So the water is going under the gate.
Yeah.
Pushing under the gate.
Yeah.
And this is the same reading, but this is through the electronic sensors. This is the electronic sensors. So they are close to the real thing outside. They are like a little bit off.
Mm-hmm.
I call the office and they don't listen to me. I told them this is what I see, a real thing.
Yeah.
And they say, oh, don't worry about it.
Because they look at the electronic data, right? So they don't believe it.
No, they don't believe it. They say, oh,
All right. Let me stop sharing. There we go. All right. We'll go ahead and pass it off to Sean, unless Brian, was there any final thoughts you'd like to get off from your presentation that maybe didn't come across in the video?
No, I figured that would give us something to go on. So let's hear what Sean had. He can rebut that or present something on his own. Curious to see what he has to say.
All right. Pass it off to Sean.
A lot.
You're muted, by the
All
way.
right,
I unmuted you right now.
Hey, at least you know you're on it. There's definitely a lot to unpack from those. I guess we can kind of go down that list and see where we get to by the end of it. That first video, the first part you showed, that was showing the flight path where you contributed it to traveling north to get to the other location. While that was actually playing, I kind of did a little drawing. Um, if you look at this, yeah, there you go. Let's see, hang on. Yeah, perfect. If you decided that flight path on that bottom line would be traveling south, then the problem is that you are trying to contribute it to this. That's not how flight paths work. If you get a typical basketball and you draw 2 points on there and you drew that line, you're gonna obviously see it's not a straight line. If you got a E map, then you could probably draw that straight line. But I think that's why you're confused by the flight path that's shown on a globe. That isn't it traveling more north. That's it following the contour of Earth.
Did you want to go back and forth on each topic, or did you want to do a rundown and then jump back to them?
I think it'd be probably better if we did a back and forth each topic,
Okay.
since there were separate.
Brian, you're muted.
Are we doing back and forth now? Okay, sorry about that.
Yeah, it's,
yeah.
We'll just go back and forth for each of the topics.
That's a good idea. Okay, the reason I pointed that out is because that's right there by the equator, and I went to. Now, granted, all these were on the same meridian or longitude, and I'm at about, let's say, 30 degrees north. Well, it starts me off. In other words, my direct line of sight is pointing north of the longitude line where you start. And then when I went to 30 degrees south, that changed. So to me, I understand that the globe directions are kind of wonky, but shouldn't they match? And just for something like 10 miles above the equator, if it was on the equator, then I would have had to start south in the south and north in the north. The fact that it was just barely off the equator meant that I had to change my whole heading. So do you think reality works like that? You think just from a 10-mile difference, I have to head north instead of, or in the southern hemisphere, head north instead of starting off south in a direct straight line? Because what I'm trying to say is in every situation, the lines are supposed to be your direct straight line of sight. So they're curving, but in reality, they represent a direct straight path. So if you're facing a little bit north in the northern hemisphere, you're looking at Sudan at the equator, just 6,000 miles away. That's your direct line of sight if you could see around the ball. So it just doesn't seem to line up with reality, man. But,
Well, again, I would say if we were looking at, like I say, an AE map, and that same line looked the same way, I would completely understand what you're saying by moving north or moving south. But again, like I said, the problem that I'm having is I don't think you realize that if you got a ball and you drew a line on that ball, it's not going to be the straight line you say it should be. Even at the equator, that line wouldn't represent a straight line. Line segment, you wouldn't be able to draw a straight line. It would have a curl. I mean, this picture that I showed, this one, the equator, that solid line, the equator is going to be like that, right? It's not going to be a straight line like the dotted line on the top. Even if that straight line on the top is going around the sphere, it's not going to be a straight line.
yeah, I get it.
And that is okay. So that's why
But here's my problem.
you see but hang on. But when you see a flight path and that plane and you're seeing that flight path, it's not a changing of heading. That's a straight heading still. But it's a contour of Earth that it has to still make around. So that straight line that you think should be there isn't going to be just a straight circle.
Yeah, that was kind of confusing the way I laid it out too. Let me try something different. Okay, so let's say this. Let's say I'm at 30 degrees north, right on the coast of the Atlantic Ocean. Okay, and I want to look at Sudan. It's right by the equator.
Hey,
Okay,
hey,
if I'm
one
looking at
sec,
my
one sec. Hey, Demon, hang on one sec. Demon, can you pop up that video? Don't start it, but just so we can see the globe and the angle
Yep.
or the latitude longitude line.
yeah,
So
good
when he's
idea.
talking, we can.
That is a great idea. Yeah, you just pull it up and you ain't even got to hit play. It should be on there.
Pop up an image of the Latin long. Okay, yeah.
Well, no, it's actually if you pop up
Yeah,
my,
hold on.
my
I
first
need to get
video.
closer.
If you put my first video without hitting play, it should be on the front page.
Yeah.
That's actually a good idea, but and I could
All
make
right,
my point
just give me
probably
a
a little bit
second here.
better.
I'll get to it.
Yes, sir. We're working him tonight, Sean.
He's still learning. Still learning.
But
He
just
has
so
to
we have
reach the,
something to
the
go,
mouse controller.
Don't you dare.
so we have something to go by. So I'm like, so the point is let's just go by a compass. We're holding a compass. We're standing on the beach at 30 degrees north and off the coast of
Sudan, near the
Florida,
equator in Africa.
right
So
there.
it
You can
looks
hit
like we have to travel north. That's
Mute
right
that
there.
side.
Stop right there. Perfect.
Yep, perfect.
Okay, so to get to Sudan from where I'm at, that is so perfect. Thank you very much. So let's just say I'm looking at the compass and I'm standing on the shoreline at Jacksonville, Florida. So the point is yeah, that's a wonky line. I get all that, but the direction I'm looking is going to be a little bit north of east, according to my compass, to look directly at Sudan. I granted, I get it that we'd have to see around the curve, but my direct straight line of sight. You realize that Google Earth only draws great circles, straight line
Yes.
routes. And so if
Yes.
I'm holding my compass, I'm looking north of east to look at Sudan. Now, I was thinking, so now if I lowered that by 10 miles, instead of looking at Sudan, I just looked at let's say South Sudan, and it's right on the equator. Then all of a sudden it would change. It and here, the problem is if you're in the southern hemisphere to look at Sudan, you should have to look south. I mean, wouldn't it mirror the north? If I'm looking slightly north of east at 30 north, shouldn't I look slightly south of east at 30 south? What's different between the northern hemisphere and the southern hemisphere?
Well, it'd be the shape. It would literally be the shape. It would just invert itself. Again, the problem that I see, I don't know exactly if this is the issue, but this is what I'm getting that your issue may be, is that flight path that does go above the 30 line. It's not actually going north of that 30 line. That line that you're looking at there is representing it being on a globe on, you're gonna love this, Demon, on a 2D surface. So it still has to account for the time travel and the distance. So that line is still representing a curvature along the 30th parallel. You
Oh,
see how that kind of
whoa, whoa.
works?
Okay, I got you. I got you. So you're I still have a slight problem, but that does clear something up. So in other words, that if I plotted my route, I wouldn't follow that line. I would be south of 30 when I first started. Is that what you're saying?
Okay. Yeah. Okay. So if you were given a heading, right, to get there, perfect. If you were given a heading to get there, and you took your heading and you mapped it out, your map would look like that. But when you take that heading, it's not going to be traveling higher longitude. You would just be taking a heading. That would be your reference. So a better example would be you could travel along that 30 parallel, right? And it would take you to where you're going. But if you're representing it on a map, you're going to be doing that, what you see there, but it's following your headings. That's why the headings are so important. And that line really isn't important at all. Because in a plane, you're not following that path. In a plane, you're following a heading. And that is representing that distance that you would have to take to do that heading on a globe. The same reason on an AE map, that line is just a plain and simple straight line. But if you were doing your actual heading, even on the AE map, it wouldn't be a straight line. It would follow the contour of the AE map. You know how the lines looks like donuts? It's just bigger and bigger and bigger. it would still follow the contours of Earth. It would have to. Otherwise, those lines don't represent anything in reality.
Okay, if I could share my screen, or never mind. Sean, I just double checked that, and I went to Google Earth, and I drew the same line out, and I moved the globe down so that line appeared straight, and it's still traveling above the 30. So that line doesn't change no matter how you turn it, even if you straighten out that line. So, but I do see what you're saying.
No,
It
yeah,
is a crazy,
it's not going to
kind of a
change.
crazy point.
It's not
It's
going
hard
to.
to explain the point.
Well, you got to remember this. The reason it does it is because it's representing a heading on a globe that is on a flat surface for you. So it's still
Yeah,
going to give you it's so going to make that distance work. Here's a better example. When you use Google Maps and you go Florida to Sudan on your map, you just zoom out. It's not going to give you those contours. It doesn't need to. It does it for you. So the distances make sense. But if you did the same distances on a globe, like you got a model globe and you scaled it out correctly, you're going to find that it has the same distance that Google Maps does.
yeah. But let me clear this up though. If I'm leaving 30 north, 80 meridian, and I'm heading to Sudan, and I'm looking at my compass at the beginning of the trip, I do indeed head slight north of east, and I do go up. If I travel a straight line to Sudan on a globe, I do go up to about 37 degrees north, or actually about 38 degrees north at the peak, and then it starts curving down. That would be a straight line on a globe, and that is to me, I don't see how that works in reality. But
Oh,
then the further north,
well,
here's
yeah.
another thing: that if I go further north, then I start off traveling even further, a more northerly direction. It's just kind of wonky. It doesn't seem to. I'd have to test that. I need an airplane, Sean. Can you help me with that?
Well, hang on, because I just realized something in my head that maybe I was explaining wrong. Yeah. Okay, so here's my little picture again. So I'll throw that up there to me real quick. Okay, so obviously you can't do a straight line on a globe, right? I mean, we're both in agreement to that, right, Brian? There's no argument about that.
Yeah, but we can walk a straight line in
So,
reality, right?
yeah, of course. So the darker line that I just drew in the middle of the two lines, that would be essentially the shortest path on a globe. So see how you would think
Yeah, the great
staying on that
does.
bottom. So if I wanted to get to those dots on the bottom line, you would think traveling the bottom line would be the fastest way. But on a globe, actually going that the middle line is actually the right way to go. So I guess in a sense, my explanation in the beginning was kind of malformed, and I've now refined it better.
Yeah, I
That would be the
understand what you're
fat,
saying. It
right? But hang
doesn't.
on,
Go ahead.
but okay, but you agree that middle line to those two dots is the fastest way on a sphere-shaped object,
Yeah,
correct?
yeah, great. It's a direct line on a globe. Yeah, I do agree. It is wonky, and there's still a little contention. But I mean, it's kind of a tough one to explain without a whole bunch of visuals, you know. But I'm,
Look, there's a
that was
visual
from
right
a
here.
previous debate with Ruif. Real quick, that was from a previous debate with Ruif. I pulled that clip out, and we just left it at yeah, the directions are kind of wonky on the globe. They're a little bit counterintuitive, and so I guess
Well, I don't think.
still my main problem is this: in the north, I head a little bit north of east, and in the south along the same meridian, I also head a little bit north of east. To me, it should be the same in the south. I should, if it's a little bit north of east at 30 north, then it should be a little bit south of east at 30 south, and it didn't match on Google Earth. So that was my main problem. But
Well,
we can skip
well,
if you like, man.
but remember, I'll even draw the line. I'll draw big lines on in the south. So it looks like a mouth, right? in the south, the bottom line is the bottom route is going to be the fastest route, right? Isn't that what you're trying to say? And the further
But
you go away from the
when I
yeah,
went to
but
30
the
south to
further
get to
away, hang on,
Sudan,
the further away you get from the equator, the more that weird wonky heading you're talking about is going to get, because you are following the contours of a globe. It's not
I
going to be
get
a
that.
straight
I
line,
get that.
so it has to be
Let
represented.
me say it
Okay,
like this. Let
okay.
me say it like this. Here's why it did that. Okay, for anybody who's wondering, like, because obviously it should match, but here's the reason it did that is because Sudan is just slightly above the equator. If it had been directly on the equator, then I would have had to head the same direction at 30 north and 30 south. But the fact that it was just about 10, 20, 15 miles above the equator, that changed the shit, right? It didn't change the north enough, but it did change the south. But here's the thing. So you're telling me that in the south, if I lowered my destination by 10 miles, all of a sudden I got to change my heading instead of south of east. I gotta start heading north of east on a globe. Like that just doesn't seem to line up with reality. Just moving 10 miles shouldn't change my compass direction any degrees at all. Not even a full degree, but much less 4 or 5 degrees, like on Google Earth.
It,
It's just a little bit counterintuitive,
it,
man. I'll leave it at that.
it, it would definitely matter the distance. And again, um, there's a difference between the geometry you're going to be doing on an AE map to figure this out. Which actually no, to do with this on a point to point, a point to point type situation. If you're doing point to point, then what you're saying makes sense. Any other route besides that line you see right there is pointless. Get it? Um, but on a globe, on a contoured surface, those lines have to be wonky because there's no straight lines on it. There's no confusion in it. I think because of the fact that it's not on the equator, is another reason why it seems so wonky to you. Closer to the equator
What'd
you
you
get, the
say?
less that line's going to get wonky.
What'd you say, John? Pun Nintendo? Just kidding. But
um,
yeah, I'll
but
say this,
I
man.
just
Let's skip this subject, man. This is kind of a me and Rio
okay.
kind of skip past it 'cause we could go on all day about these damn directions and all this stuff. Let's talk about this, man.
Okay.
I'll bring up a good point, and I'd like to hear what you have to say about this. Um, the reason that we got for the laser beam experiments and whatnot, and like black swan and other miscellaneous long distance observations was refraction. And we got a couple demonstrations from the Glober. The one I showed was Mick West, where he put sugar in the fish tank to make the density gradient, to make the light bend downward, and shows it with the laser, shows the actual laser curving downward. So for the longest time, I was arguing that the light's refracting upward, making things appear lower. But then when I really took a close look at that video, I seen that when he added the sugar water, even if it's the way that he describes it, and it's working exactly the way where light is bending downward, if it is denser lower down, then even using that and granting all that, it made the bottom of the city skyline disappear, which is what we see sometimes when we look out. There's often days here in Florida where if I look long distances, I can see the bottom cut off. It's usually mirage, but sometimes it doesn't happen. But when it does, that sugar water experiment gives a perfect flat Earth explanation. If that's the way refraction works in reality, with straight line of sight, we lost the entire bottom half of the city skyline. So wouldn't that be a good flat Earth demonstration instead of globe? What do you say to that?
Okay. The main thing, because you're talking in reference to the video you were showing, or I'm talking in reference to the video you're showing, which I think is the same. One of the main things that you got to remember is the reason we do those tests in a fish tank is we want the most drastic results as we possibly can get, because we only have so much room. So when you add if you make that medium a lot more dense, you're obviously going to see the light bend a lot more. Um, it would be in the same reference as, well, with all this room in between you on Earth and all the atmosphere in between us, we're not expecting it to be as drastic as in the fish tank, but we do know that it's going to happen. We kind of know that by how light works. And I'm trying to find, because I had to write some notes down. When you were talking about, you were kind of using one of the sunrises, I think it was, examples, where you were saying you look to the left at the moon's lit up, dark sky. You look to
Oh,
your
no, no,
right,
no, 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 no,
and
no. That was selenelium. So sorry, Sean. That was in selenelium. I was going to save that topic for later. This was it
okay.
does kind of lead to that though. I mean, I'm sorry to interrupt, but this was about would you agree that in the fish tank, I mean, wasn't it pretty obvious that whatever was happening, compression, refraction, we did lose the bottom of the city. Would you agree with that?
Okay, but when we're talking in reference to that median and how light works. You were saying a minute ago. I'm going to ask you, which way did light was light traveling in that in that experiment or test?
Yeah, I'd say it was definitely bending down. He demonstrated that with an actual laser
Okay,
that I cut out.
okay, okay. But with the view of the city line, for example, it's kind of hard to dissect whether or not what's happening in that because you're just showing it high and level. The only thing I could devise from that was I would need to know that the tank and the screen is at the same height. Otherwise, I can't really talk about that one. But the realization is that the when we're looking at refraction and how it works with things in the distance, I know people hate this. Black Swan's a perfect example of this. Um, I guess my next question would be in the Black Swan, with the way the globe explains it, do you think the light's traveling up or down from
Well,
the back
the
front?
way the globe explains it, it would have to be the way the globe explains it is the light bends downward towards the denser gradient, making things appear higher. And my question would be that why just the oil rig? Why not the water in front of it as well? Because there's water directly
It
in
does.
front of it. It's supposed to be blocking it, but it's lower. So what you're saying is the oil rig
Okay,
rises up, and the water right in front of it doesn't.
it does. Because if you look in the Black Swan picture, I wish you had that, Demon Strive. What you would see around on the sides, just in front, kind of, is water. The reason you don't see the water in between is that there's this thing in front of it that's closer to you, which is the actual apparent horizon. So everything beyond that point that is being obstructed is being loomed up, and the light is hitting coming down to your eyes. I mean, we don't. I don't even think we're in contention about how light works in these denser medians, but that would be a perfect example of why you're not seeing a body of water like you would think you would see in our explanation. You would see our apparent horizon, and then a ramping of water to the next platform, right? That's what you're thinking the globe, with the way the globe explains it, what you think you should see, right? By the water in front of it.
Yeah, man. Yeah, I mean, I could
Mhm.
grant you that for the sake of conversation if you want to make a point or finish your point.
Okay, okay. Okay. Well, the point of that is the reason you're not seeing that is still because of curvature. Well, the way we understand how light works, to give it a quantifying amount of obstruction, the only way you could possibly even do that is if you increase the median way far beyond the quantum amount on Earth, right? In our atmosphere in between you and an object. That's why we do the fish tank thing. So we can see, remember that high quantity of action happening, a lot of bending of light. The picture he's showing right now, if the median's thick enough, it's going to be able to do it. But again, what you're looking at there would be on Earth in our observations, the most extreme possible view you'd ever get. That's not the
Yeah,
black
yeah,
swan.
yeah.
Black swan
That,
is
that
an
is the
extreme
globe.
view.
That is the globe explanation. But what? Here's the crazy thing though, is I do a lot of long distance photography myself, and I went out and bought a P1000 when I first heard about this stuff, and when we get days like that, such a nice crystal clear day. You know you're going to see far, and you're just praying on the way there that no mirage, please, because it's usually an inferior mirage almost every day, and you're just praying for no mirage on a good clear day like that. You know you're going to see far, and that's the days that the globe has to stay. There's extreme refraction happening. So like say with the bent
No,
oil
no, wait,
with the arm.
hang on,
Yeah, go ahead.
hang on. One second. You said the globe model says that on those clear days when you can see further, that's when there's the most refraction. That's not what the globe says, though.
Yeah, it
That would
has
be
to
what
be.
we would consider. No. We would consider a clear day with minimal atmospheric conditions in between you and the object as a low index of refraction. There's the least amount of refraction that you're going to get for that a day. That would be the best case scenario. The days where you're seeing miraging happening in between you and that object are going to be higher on the index of refraction level. Those levels indicate how light would bend through the atmosphere between you and an object. That's what the globe says.
Well, I'll say this: in reality, man, it's impossible to predict inferior mirages because they're so common. but I'll say this: that's counterintuitive
but if
with
there,
reality, bro. Trust me, what you're saying does not line up with reality, not completely.
it it does. I can
That's what we would
I'm
expect, but that's not
pretty
what we're
sure.
seeing.
Okay, but the problem is that is what we see. What I'm explaining right now isn't a logic walkthrough. It's observation. I can give you a perfect example of this. You know, plain truth, Travis. Um,
Yeah,
we
real good.
did a
Yeah,
observation off the.
met
Yep,
him in person.
yep. Me too. We did a observation off the California coast together. We observed a oil platform um, at nine. It was at 9.6 miles. Behind that was a cargo ship that was at 13.9 miles. We were able to get those locations based on, Google Maps was the easiest way to do it for the platform. But for the ship, we were able to go on Ship Finder, which shows you the channel that the boats run through. We were able to locate that and identify the boat and distinguish its distance. Along with that, we were able to get the water temperature every 5 miles through buoy information that you get on Ship Tracker. With that, it also has air temperatures at 10 feet. So, with all that data, we're able to see if the conditions of the water and the air are going to give us more than likely an inferior mirage or some type of atmospheric condition, or it's going to be a good situation where less things are going to play factors in our observation. And in that observation, there was that cargo ship had 55 feet missing. Um, the reason I bring this up is with Earth curvature, the amount of obstruction, even with applying any kind of refraction because conditions happen, period, right? Um, you wouldn't be able to quantify the 55 feet that were missing on that ship with only atmospheric condition. That's where the
Okay.
problem starts. That's why when you
So
start talking
here
about
would be my
refraction, bringing things
yeah,
up,
yeah.
well, hang on, when you bring refraction, bringing things higher or lower on a globe, you have to remember that you're talking about a flat Earth where these situations shouldn't be happening at all.
You say that, okay. Now let me rebut that. You say that, but if you look right next to you, okay, this is with light doing exactly what you say. And this is on a flat fish tank. Okay, the bottom of this fish tank is flat. We have a direct line of sight. And just by adding sugar, we cut off the bottom of the city. Okay, so you're saying words, but right next to you is evidence of reality, just kind of smacking you in the face. Sorry, to put it so blatantly, but right in front
Okay.
of you is a direct line of sight and half the city missing. So maybe that's what
Okay.
refraction is.
Here's the problem with what you're saying. You're comparing a situation that you have to make extreme to do something. Our atmosphere doesn't act like that fish tank. So again, what would be quantitative effect through refraction that does that on Earth, where we know the atmosphere doesn't get as dense as that fish tank? So
No,
what
so
you're telling me
you
is,
disregard.
hang
So
on,
are you
what you're
throwing out this?
hang on, well, hang on. What you're telling me is what I was explaining isn't reality, and then you're telling me to look at the example you're giving us, and you're saying that's reality. The problem is that fish tank is so far from reality, it is not reality. You had to make that water like that to get the react to the effect that you got, right?
Yeah, I see what you're saying. But do you agree that the light is definitely bending down? The light coming to the camera or our eyes is refracting downward, and instead of the city
Mm,
appearing higher, which is what was said to be explained. He was talking about a laser, but he missed the elephant in the room. What happened is he literally cut off the bottom of the city. So if light is doing what you say, then we're missing the bottom of the city skyline just by adding sugar and forcing the light to
okay,
do what you say it does.
okay. So this is what's happening. Because you are changing the median between you, the screen, and the atmosphere between the screen and that tank, um, in the tank itself. I wasn't going to say anything, but no, you got to put that picture back up. It's very important. Um, the one way other reason I'm going to consider this one, impossible atmosphere, and two, impossible medians in between our atmosphere is if you look at that screen in your city, along the sides of your city line. See how bent those are?
Yeah, I'll grant you
Which way?
the crazy
Mhm.
conditions. Yeah, I'll grant you that.
Yeah, and I can see all of the screen is doing that. So I would contribute that the bending of the light through the thick dense medium you've introduced to the observation is going to do that. If you want to show me a real world experience of this, I would use a clear water, no sugar in it, and do the same test, leveling out the surface of the tank and that screen. That would show me what you're saying is correct. Otherwise, all you're doing is making the effect happen. This isn't real world, what
Sure,
you're showing me
sure.
right now.
That was the intention. That was the intention. And but
Okay?
can I get at least one concession? So, do you
Yes.
agree that by adding the sugar, whatever the hell's happening, whatever's causing it, by adding the sugar and forcing whatever refraction or whatever, it does cut off the bottom of shit.
Okay. Oh, perfect. Okay. I will tell you right now, Brian. Um, Obstruction, physical earth, is not the only thing that can account for obstruction. There is refractive qualities that do obstruct objects. Yes. Problem is the quantitative amount of effect of it. If we were talking about a foot of something being missing at 3 miles, I would absolutely give you refraction, um, high index of refraction, atmospheric conditions occur causing that obstruction. But again, like I talked about with that cargo ship, when you have 55 feet of obstruction, for this one example, you no longer can show me a quantitative amount of refraction that it would take. It would take more sugar in Earth's atmosphere than you have in that tank to make that happen.
Yeah, okay. So you don't, but you still didn't answer the question. You agree that
I did.
whatever's happening, we are missing. It does cut off the bottom of the skyline or the shit we're looking at.
I did answer it. Again, refraction does play a part in obstructing things. A quantitative amount, absolutely not.
So we're
When
not
I
seeing
say,
less than the bottom of the city skyline.
yeah, yeah, again, you are not showing a real world example. You are showing an example of where you have controlled the median so much that light changes its direction like more drastically.
I'll
If
grant you
we're
that.
talking real
Look,
world, okay, yeah, yeah. So if we're talking real
I'll
world,
stop pulling. I'll stop
then
trying to pull teeth, bro. Trying to get a concession is pretty hard, bro. I'm trying to just
oh
see
no,
if
no,
we can
no.
find
Again,
out.
no. Hang on. Again, I'll make it clear. Yes, refraction can play a part in obstruction, but there's a caveat to that. The quantitative amount is not enough to show what we observe in reality. So I am conceding to you. Refraction does play a part.
Fair enough. Here's something else to ponder. Okay, I almost put this in my presentations, but I left it out. These are other demonstrations. You know, flat earth is like, you know us. We like to show shit and show possibilities, whether that's happening. You know, that's what we're discussing. But so Pebbles on the Pond, you're a veteran. You're probably familiar with this. But anybody who isn't, he set up in a warehouse in the winter, and he set the camera on the ground. The center of the lens, I think, was about 1 inch above the warehouse floor, and he set up a light, three lights. One of them directly in front of the camera at 1 inch, one at 2 inches, and one at like 3.5 inches. And then what he did is he opened the warehouse door and let the cold air in. And what happened is with the camera recording, we watched the bottom light disappear first from bottom up, and then the second light disappeared, and then the third light it started to kind of disappear a little, but it wasn't enough over that distance, but it kind of started to disappear a little bit. But the bottom two lights disappeared right in front of the camera with just a little cold air, meaning, and you can also you can do this by he could have also heated up the warehouse floor. If you could take a torch and do it on your driveway, if you don't believe me, it's easy. Just heat up your driveway or do it during the heat of the day and throw a bucket of cold water on it and you'll see a reverse effect. But the fact of the matter is when the warmer bottom and the colder top, when you let the cold air in, it did cause a refraction. And what was right in front of the camera, in fact, disappeared. And I would say that this is what happened. So we get the most refraction during the heat of the day when the sun is at its highest, and right after, like between like let's say 11 and 3 o'clock in the afternoon. When surveyors say that's really the only time they do um, observations for geodetic, and I would argue that that's the worst time because the sun is heating up the water in the ground or whatnot, and it causing the refraction. If you look at Skunk Bay, there's not too much going on until about 10:30, 11 a.m. And then you start seeing shit bounce around between like 11 a.m. and like 3, 4 o'clock in the afternoon. And then when the sun starts receding, it starts calming back down. So that's a lot to
Okay,
unpack.
okay, yeah, okay. So, well, I'm gonna go backwards, kind of. So it's the Skunk Bay one, and surveyors. Skunk Bay doesn't things don't get wonky until about 2:30, 3 o'clock until sunset. For a surveyor, there's a multitude of hours and times of the day where surveying's perfectly fine to do it. The reason noon is usually the witching hour is because light its direction isn't in your face. There's less atmosphere between you and the earth and the sun to affect the observations. Some does still happen. Not saying it doesn't, but your understanding of when surveying is good is based wrong. Dusk and dawn are your worst times. It's not even worth doing at dusk and dawn. Um, let me see if I can remember. Again, the examples that you keep giving are not real world observations. They're not observations that explain anything. Every time you're talking about these examples, Brian, you're having to make an extreme effect to your observation to make things happen. And there's no part of this argument that I'm
Okay.
arguing against that. You're right. If
Well,
I
that's
change
good. But
hang on, if I change the air, the light, the median, anything in my observations, in my experiment or test, the first thing you got to understand is you are not making real world choices. What you're doing
okay.
is you're making
Uh,
these extreme effects happen so they cannot explain what's happening
sure,
when you
sure.
make an observation on Earth.
Yeah, I heard you, man. And my alternative would be doing nothing at all. Another example I could give, another real world example besides the warehouse floor, and trying to force effect. You know what y'all say is causing it. We're trying to force them. And another
Mhm.
real world example would be Sky Free, where he shows his little RC boat, and he shows like him going like 600, 700 feet in the bottom of his little battleship, and he shows a actual ship on the horizon where the bottom's cut off on days where that happens, and on days it happens in the lake where there's supposedly like a little half a millimeter of earth curve, and we're missing half of his little battleship. That's with nominal, just regular atmosphere. So you're saying
Okay.
we're not giving real world examples. Well, my alternative would be to do nothing at all. Can you give me some globe Earth examples of replicating something in the distance? What's happening in the distance?
Uh,
Can you give me some globe examples?
yeah. Globe observations. Before we do that, I want to ask you a question. Again, you conceded to the fact that these experiments and tests that you're talking about are pushing the limits to the extreme, and because of that,
Yeah, the sugar water.
because of that, yeah, because of that, you're not talking about real world things. So here's my important question to it. You want me to give you real world example? The first thing would be this: when we see on the globe model, I'm going to use black swan as an example. You conceded to the fact that the light is actually going down to your eyes.
Yeah, well, let me ask real quick. So the arm that's bending in the black swan, it's refracting downward. It's actually the fire boom. Everyone has it where on that particular crane, there's a constant fire lit, so it's always refracted. In most videos, you'll see it refracted unless the wind's just blowing it directly away from the camera. Well, that arm is bent down, and I've told you the actual real life cause. But since we're talking globe model, uh, so in reality, would you say that's closer to the actual position of the oil rig would be the arm that's bent down? Would you claim that's closer to the real world position, or the oil rig
No,
itself? Which is closer to the
no.
real world position?
The light going up to your eyes.
Yeah,
That's the crux of this argument.
yeah, no, I'm saying the way we see it is one thing, but the one crane looks a little lower, and the rest of the oil rig,
It is lower.
compared to the rest of the oil rig. to what you say is that the oil
distorted.
rig's being loomed up or 7/6R. So we're seeing the oil rig up higher, and the water right in front of it that's usually blocking it is not uh, going up. It's just the oil rig, not the water. So would you say that arm bending
It's
down is closer to its actual position, not its apparent position?
again, it's not only the oil platform that's being loomed up, it's also the water around it. The reason the water in front of it isn't also being loomed up is because it's much closer and obviously outside of that turbulent air. So the reason that you're not seeing in between water is because it's closer. The other reason you're seeing that is there's this whole thing called a body of water in front of it.
Yeah.
The
Wait.
the
What about the
actual
water touching it, or just like 1 inch in front of it? So how? I mean, just
the
that 1 inch.
platform
Yeah, just the water being
of the
1 inch
plat
closer. Is that what you're saying? That just it's
yeah, yeah.
closer.
If
So
you look at the
just
black
1 inch closer
Brian,
is not blocking it.
if you look if you look at the black swan picture, you see water around that platform. The reason you don't see water in front of it is because the actual apparent horizon is still there. You're not seeing the object. You are seeing the light coming down to your eyes or coming up to your eyes. I apologize.
Hey, I wonder how far you'd go to back this up. Like, I know you're an ex-flat or whatever, so you were partially woke. We'll call it you were sleepwalking. But so
That's
what would you take
well.
on
See, that's
that?
the best
Wait,
part.
real quick, it's
That
funny.
hang
Would
on.
you
That's the best. Hang on. I want to respond to that dig you
yeah,
just
go
had.
ahead.
The best part about me being an ex flat earther is that you're right. I'm not coming at you with just an understanding of what I've been told on the globe model. What I'm actually doing is I'm actually comparing what should happen on a flat Earth and a globe model because I've had to try to do that before. So again,
You
you
can't
can say
replicate it in
certain
globe
things are
Earth,
wrong.
though.
You can
You just give me words,
no,
pal.
you can. No, you can replicate it. Here's exactly how you do it. You get a fish tank, you get water, you put a lot of sugar in that water, and you can see that how light bends, right? You can see that light bends down to the denser medium. Am I correct, Brian?
Yeah, and you see the bottom of
Uh,
cities
perfect,
disappearing.
perfect. So if I'm making an observation on Earth and I see an object that here's the key word I don't normally see, Brian, and I see that object, I can use the idea of I knowing how light works, and I know that object is not normally being seen. So I can say that between me and that object, the atmosphere is obviously turbulent enough, the index of refraction is high enough that obviously the light is doing this, and this is why I'm seeing an object. You've already agreed how light works. I'm not understanding where I'm having to reach to explain this to you.
Well, this is why, because that's just it. What I showed earlier was exactly what you just said, sugar water. This was supposed to be a globe demonstration, and he missed the elephant in the room. What we were supposed to see is things get higher, but what we've seen in reality was was the refraction cutting the bottom of shit off. So what's happening in reality over the flat bottom fish tank is on days where we do get obstruction, there's fucking refraction, Sean. I mean, he's showing it in the fish tank,
How
dude.
many?
With
Okay,
you
I'll tell
increase
you
the
right now.
refraction, and all of a sudden the bottom of stuff
I,
starts disappearing, bro. You know?
Yeah, I'll tell you exactly why that happened, and I'll even explain to you why I brought it up earlier, Brian. Remember those sides and the straight lines around that skyline that you showed in that picture? Remember that? Remember how the sides were bent? That means I know two things now. One, the median between you and that object or that screen have changed dramatically. But here's the even better part. I know that light that was showing the camera to the screen, I know for a fact that light was doing a bunch of wonky ass things. I know that because the lines were all distorted like that platform. But here's the most important thing. You didn't let that sugar settle for at least a half a second. It looks like that sugar was put in instantly. You want to know how I know? Because the whole tank was affected by it. Remember, the
Yeah.
denser medium, things settle.
You said he
There
added
was
it the
no
night
layers in
before.
that. There was no layers in that tank.
I have seen
That's
what
the
you're
problem.
referring to. Like I have seen what you're referring to, so I'm not going to lie. Like I've seen it after I've seen one demonstration where after it settled, some things did appear higher, but usually that's not what we see. And Mick West said that that was the next day when he actually recorded that. So it did settle. So we do get, in all fairness, we do get
Again,
mixed. We do get
it's
mixed
not an
optics.
example, but it's not an
This is a,
example of the globe. It's not an example of globe
let me finish
observations
real quick. Let
because
me finish
you
real
are
quick, John.
all
Yeah,
you're
yeah,
doing
Sean.
with that fish tank
Let's let
is
Brian
showing
finish
how
though.
light works.
Yeah.
Yeah, let me finish. Let me finish my point. I'm trying to be fair. We have seen mixed optics in the fish tank, but I will say this: for any listeners who haven't seen this, or any new listeners just who happen to come across this, that sugar water with all the crazy shit he's explaining is not that much reality. That is a globe demonstration that backfired on him, and the demonstrations we give are with actual air and are over little calm lakes, over 700 feet. We give real world examples of what you're seeing in the distance, and it's indisputable, man. You can just, I mean, I could still go with the globe and say, well, it just disregard demonstrations of real world happenings, but and choose to listen to men with words. But I prefer demonstrations and observations myself, man. Go ahead.
Again, that test wasn't to show what we see on the globe. It is literally a test that shows how light works through different medians. I don't know why you're doing that. The test definitely was not done by a Glover to show why we see obstruction. It's not even a backfire. All a test using a fish tank and sugar and a laser light, anything like that, especially the ones you showed, are only to show that we understand how light bends, that it does bend. That's all that is. It's not a
Yeah, yeah,
comparison to the Earth.
I agree. He was demonstrating like why we see lasers over these long distances. He's trying. It was at least an attempt. At least he tried to do a demonstration. But like I said, he
Okay,
missed the elephant in the room. And one more thing, as
go
what he
ahead.
did show. Go ahead, Sean. Go ahead.
Well, I just want you to understand that, yeah, or at least concede to the fact that your last statement that the globe isn't showing real world things and the flat Earth is was a complete just misrepresentation of what that test actually even about.
I just said that
Do you have
yeah. Go ahead.
can I just interject here for a second? You said you had a list of other things from his presentation. Maybe we could move on to one of the other
Yeah, we are
ones
getting
Well,
we are getting hung up on this
wrap
one. You
wrap
want to talk
it up.
about the Selenelian, John, or what? Yeah, we are getting hung up
I
on
would
that one.
I'd like to jump to the canal one is actually super simple. Um, there was a couple statements that the guy made. I know the guy, so I know exactly what he was trying to say. Um, maybe I'll just run over them really quick. Okay, perfect. You understand, Brian, that canal is man-made, right?
Yeah, it's an aquifer in California. Yeah.
Okay. You understand there are channels within that canal.
Yeah, in that particular area, they're closely spaced, like within a couple of miles, and then in the sticks, they kind of spread them out a little bit. But yeah, in that area,
Mhm.
the gates are about
Yep.
2 miles
Okay.
apart.
Okay. And in between those channels are pump houses. Remember, he showed us that pump house.
Yep. And at each
Okay.
gate,
And now, what did he use to show there was no curvature? He used the water levels in between those channels. And let me make it clear. He never once explained that they were in channels controlled by pump houses, engineered for flow,
okay.
right?
Well,
Then
yeah, but
and
they
then
open up at certain
hang
times.
on. Yeah, yeah, I know. And then he brought up the borders, the concrete borders that run along the side. And he said that supposedly they follow curvature of Earth. That is not true. It accounts for
Benchmark from the
curvature
surveys.
in its
Sean,
in it. What?
he literally shows the benchmark in that video. I didn't show it in my shortening, but he literally shows the pins from the benchmarks from surveyors right there
Okay. Yeah.
at the top of the dam. And here's the thing: they do open the gates. It's like a dam. When the water hits a certain height, they open the gates, and yeah, you can see water flow. But usually they're closed.
Mhm. Again, I'll make this clear. Yes, he does show those data points, but I'll make perfect right there. So when you're going along that edge, that border, concrete border, this is what they do. They take the profile of curvature and equate it to make sure there's enough for a certain amount of percentage of fall at any given time. Remember, this canal is engineered to flow. So again, it doesn't follow curvature, because if it followed curvature, it'd be wonky. Remember, we don't
Yeah,
live on curvature.
it's all in there. It's all in there, Sean.
Okay,
It's
perfect.
3 to 4 inches, 3 to 4 inches per mile. I mean per gate. They add
Mhm.
like 3 to 4 inches for flow, and that's what we
Exactly.
expected. That's
So
what we expected, because when
okay,
he measured the top, and he measured between the gates, and he had a good steep angle. He didn't have no little, like a long bullshit angle. He had a good steep angle all the way across, and it did show the 3 to 4 inches plus the 8 inches per mile we would expect on a globe. He was disappointed at first,
so
because it was built to match Earth curve, but what happened when he measured the water is that
let,
it was more than that.
again, you can't measure the water because the water is in channels. It doesn't follow the contours of the whole canal. It's controlled. That's what the pump houses are for. Again, you said something just now that was very weird. Again, the border of that canal is engineered to flow at 3 inches, about 3 inches a mile. About one, that's not the contour. That's not following curvature, because we know the curvature is a little bit more than that per mile. So again, it's not following the curvature. It is only engineered to drain with that curvature in mind, so that it's not all wonky.
Right,
So
but what
again,
would we
let's make this.
expect? Let me ask you a question real quick, so I know where you're coming from. What would we expect if they built the aquifer, and they built it, and they added in earth curve per mile, so it's not accumulating. They're doing this in between shots, so it's going to be per mile. And what would you expect the water to do if, and because
Not
that
flow
particular
fast enough.
section, well, that that particular section curves, it loops around a little bit, so it winds up being a just barely over 1 mile distance, and actual real space distance. The length of it's 2 miles, but like I said, it curves around, and it's a little over 1 mile. So what would you expect if you added earth curve, you added extra drop to the elevation, plus 4 inches of actual flow? What would you expect the water to do? How much higher would you expect it to be if the Earth was flat? If they added 4 inches, and plus they added 8 inches for Earth curve that was non-existent, how much higher would you expect the water to be if the Earth was flat?
Well, problem with that question is you just asked me to clarify two different scenarios with one scenario. I'll make it a little easier for you. If you watch that video, Brian, I'm sure you watched it. Um, Towards the end of that canal, how often do you see that canal within a berm?
That's a pretty good berm. It's not straight hardly in no places that I've seen.
Oh, it's not supposed to be straight. The berm is the border of that canal. Now, here's the reason they have that berm, because 3 inches per mile is not as much of a curvature as 8 inches per mile. So, what I would expect on a globe is that canal would be higher than the curvature. So, therefore, you have to contain it by building berms higher than the curvature of the earth.
Sure, but how about this? On a level globe Earth, let's say if the water was stagnant, let's narrow down the variables. The water is completely stagnant in that stretch, and it's 1.25 miles of true space, true distance. Okay, and it's 4 inches of slope from one end to the other. On a globe Earth, once again, the elevation is exactly the same, and take away 4 inches. So what would we expect the water to do if it was 4 inches lower, uh, globe elevation at one end? What would we expect? How much, or what would the water be compared to the beginning? What would it be at the end? Higher or lower or the
Again,
same or what?
again, this is going to be the problem. And I'll give you the scenarios because, first of all, I cannot unpack that question because it doesn't make sense. But what I'm going to do for you is I'm going to give you the scenarios in which what that canal would do if the Earth was flat and the Earth is a globe. I hope that is answering your question. On a globe, what you would expect is the canal to slowly rise above the Earth because curvature is more drastic than the amount of drainage and fall that canal has to do. So on a globe, I would expect to see at a certain point a berm would come into play to be able to account for that. Now I'll go to a flat Earth. If we're
What
on
are
a
you talking
flat
about a
Earth
berm?
and you
Wait,
build,
you keep saying berm? What do you mean by that? So I understand what you're saying.
okay,
I thought you
the
meant
picture,
contours.
yeah, yeah. So see the top, see the top of that canal right now where the cement
Yeah,
is and the dirt
where the
next to it.
elevation, yeah, where they set the
Okay,
elevation pegs. Yeah,
now
yeah.
now if you kept walking away from that canal, what you would end up doing is walking downhill to the rest of the dirt, rest of the desert. That canal is raised above the desert floor.
Yeah, yeah, it's like 1,033 feet at that one. There's elevation markers all along it,
No, no, okay, no, no,
right on the
wait, wait.
berm.
Okay, let me make something very clear. There's two distinguishing conversations happening at once in your brain, and I need to make it so we can understand which one's being talked about. One is elevation, one is curvature. The reason the elevation has to be higher than the desert floor is because the amount of fall in the canal is less than the amount of fall in curvature.
There's no
Right now, I'm going
fall
to go
on
to
a globe, bro. If it's the same elevation, then it's level water, right? On a globe.
again,
Let me
again,
explain your model to you
again.
real quick.
No, 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 no,
If
no.
the
I don't need
elevation
you. No,
doesn't
Brian,
change,
Brian, stop.
then the
Brian,
water
Hold
stop.
level
on.
changes.
Step,
Hold
step.
on.
Brian,
All right.
I
Hold
don't
on.
need you to explain the globe model for me at
Yeah.
all.
Well,
I'm
let's separate,
explaining
not
it
step
for
on each
you.
other.
Okay. Okay.
All
Well,
right.
here's the
Hurry up
problem with
and
that.
let's get it under 20
Okay.
seconds here.
Okay. Perfect. Well, I gotta. He's cutting me off halfway between my explanation of this.
You just say I
So
cut you
anyway,
off.
I've already. Okay. Put it this way. Put it this way. I've already said the globe. I've already said the globe model. Now, if we had the same canal on a flat Earth, what would end up happening because it's engineered to flow? What would happen is this: the canal would start either at the top of a mountain, or if it started at the desert floor, it would have to start dropping gradually. So that canal wouldn't be in a berm; it'd actually be down in a canal. They'd have to dredge to make that canal work on a flat Earth to make it flow.
Yeah, that's what you just said, dude. I tried to respond and you jumped down my throat. Okay, now on a globe Earth, okay, the desert doesn't matter. They can't even replicate what they used to in the old Army Corps, like the old engineers. They had the flow down pat, dude. I don't know why we can't replicate shit like our forefathers did, but they do their best. But here's the thing: on a globe Earth is I know you understand this. I'll save the sarcasm. On a globe Earth, if the elevation remains constant, then sure it's curving, but the water also remains constant. So anybody who doesn't understand globe, I know you do, but so we don't expect drop in water in their model. It's a vector of gravity, and so that if the elevation remains constant, then the water remains constant. Okay, so that's why he checked the elevation of the water, because if it were level, which it's not built to be level, but if it were level, then the water would have remained, let's say, 7 foot from the top to the water line. Okay. Now, if it's draining last thing, if it's draining 4 inches, we would expect to measure 4 inches less, meaning the water's higher at one end. But what he measured in reality, which water flowing doesn't help you here, but was 14 inches higher water, which means instead of it was the 8 inches of a mile, which they added to the thing. So what they wound up with in reality was just a structure with more drop than was necessary, and that's why they had to add all them extra pump houses. In my opinion.
They add the pump houses so they can control the level of the water, which is why the level of the water between each section is not conducive to whether or not it's level or flat. Again, you can make that very clear. If you wanted to do this test, you would actually probably use that cement rim around it, not the water level, because again, water level is controlled by pumps and the canals themselves or the channels themselves. It is very important that you understand in the globe model, Brian, that desert floor does matter because
I think you might have
if
missed some
there
of it. You
is
just dropped out and popped back in.
okay, I'm not sure if you understand it. That you can't use the water level as your
Yeah, I caught
measurement
most of
of
that.
whether or not.
I did disappear for a second. Sorry about that, but I caught most of that. And yeah, I understand the pump houses and controlling the level, but I'm saying I don't think they needed that many. I think they would need one, every 10 to 20 miles. I think it's just my opinion. I think they added extra
Huh?
because they had
Okay.
more slope than they intended on. And I think that's why they
Can I
have the
ask
water
you?
flowing under the gate too, and on top. But that's I can't prove that.
Okay, so it is very clear that the amount of drop that the canal has versus the amount of drop of curvature does make sense. You understand that's why it's sitting
Yeah,
on a
yeah, yeah.
berm.
It does. Yeah, and the fact
Okay.
that it's 14 inches higher at one end than it is the other, and a mile a quarter, and just about a 1.25 mile distance, means that there is 14. And while the water's stagnant, means that unless the water's going to come rushing in all of a sudden when we ain't looking, then there's a 14-inch difference in elevation, whatever theirs may be, flat or globe. What the water don't lie on either. Then if there's a
Okay.
14-inch difference in the height, then there's 14 inches of slope.
All right. Hopefully you'll be able to see this. I may have to move my camera so you can see how this works. Because the problem is I don't think you understand how a canal works.
That's why I asked you. What would you expect if there's 4 inches of
I
slope? What would you expect the water to be at one end compared to the other?
oh, you can see it. Let's see which way I have it. Okay, perfect. Okay, do you see how that is laid out? Which way am I going? Hang on, let me get it so you can see it. Okay, see that line, that the top line that just slopes down?
Yeah.
Okay, do you see
Wait,
the
why are you
steps?
showing locks? Wait, why are you showing locks?
Again, because those are the channels. Those are where those pump houses are. Those are references to the pump houses. Now, I'm trying to show you this because what would happen here is that you would have such a constant flow of water that each pump houses would get overwhelmed. So what happens is where these dotted lines are, those dotted lines represent your berm. That berm that's around where that concrete edge is, that's where the dotted lines are. That's how you account for earth curvature, and you don't get too much of a flow to overwhelm those pump houses. Which is why on a globe you stand on a berm the further down you go in that fucking along that channel. Do you want me to do one for flat Earth 3 now?
No, no. I'm just asking you. What would
Very
you
simple.
expect what would you expect if the water's stagnant and there's 4 inches of slope? The model doesn't matter. Let's just say in reality, if the water is stagnant, if we have the gate closed, what would be the height difference in the water from one end to the other if there's 4 inches of slope? It's not a trick question.
You would have to measure the four corners of the canal around the water to answer that question. You could not just measure the level of water. It doesn't work that way because it's an engineered canal.
No, I'm telling you, if the water is stagnant, the gates are closed. Let's just say we have a
You're
ditch.
not listening.
I'm trying to find a way to answer
Okay.
this question, dude. Just
I'm
so
telling
we
you.
can proceed. You won't even get past step one. I don't know how we can proceed or carry on when you won't even answer a simple, like, if there's 4 inches of drop on anything, what would the water do? How much drop would there be
Elevation
from
or
one? Yeah,
elevation or
elevation.
curvature? Which one are you talking?
Elevation.
Elevation, 4 inches
Elevation.
of drop.
Yeah.
4 inches,
Yeah.
4 inches less.
On a flat or globe, right?
4 inches of elevation drop is 4 inches of elevation drop.
Right. So the water would be 4 inches higher at the lower end, right?
What?
If tub or whatever you have the water in is dropping 4 inches, okay, then we would expect from one end to the other over a mile and a quarter, or just over a mile, if it's 4 inches less elevation, we would expect the water to be
Before more
4 inches higher.
4 inches lower. 4 inches lower.
Lower.
See, I don't.
So
Why do you say higher?
let's just say we have a string
Okay,
line and it's
hang
straight
on,
as an
time out,
arrow.
time out. Hang on. I need you to ask you this question. Do you think each section of this canal is the same elevation? This is why I was specifying the steps that you say I was cutting you off about, and you were saying that I can't get past step one. What you need to
No,
understand is this:
there's
that
constant slope, bro. It's 3 to 4 inches over hundreds of miles, dude. What are you talking about?
okay, again, if there is constant slope, it makes this example make more sense if you just listen. First of all, this is an engineered canal. The first step is not measure the water level. Why? Because you've already acknowledged that the canal has an engineered flow, which means this: for the four corners of each section of the channel you're going to measure to do this test, you need to measure the elevation points of each corner, because what you'll find is that the box that you've now put this stuff in is skewed a little bit. So when you go to the other side and measure from water level to the top, it's going to be different, Brian. Just because the canal itself is engineered for flow. Forget curvature.
Okay, so you think there's locks in the aqueduct?
I didn't. There are sections of it. Yes, at each pump house there is a section, and that
Okay, and
section is an
how much
engineered.
higher are these locks? How much higher are the locks from one end to from at each gate
It's
that you
an.
think that are there?
This is an engineered fill, which means it has section channels, and for every section channel, it has an elevation datum point that represents curvature and elevation separately for flow.
Sean, when
So
they
when
show the
you're
other
telling me,
side, it's the water level. It's not a lock, bro. It's the levels are a little bit different when the gates close because of the slope, whether it's globe or flat. They're not locks, dude. You don't have the water dropping steps. It just builds up because of the slope, and they shut it down. That's why he measured from one end to the other, because he did it while the water ain't flowing, to
okay,
see if there's a difference. He didn't know. He knew what he was supposed to measure, but he didn't know what he's going to measure. It's not locks, bro.
okay, Brian, I don't know if you're waiting for me to stop talking so you can talk, or you're just not listening at all. I made it very clear. The sections, the berm, are all engineered to flow. So if you're going to measure between sections of pump houses, the level of water is not going to run the contour of the whole
Okay.
canal. So
Okay.
when you
Well,
measure just the
no, go ahead. I
Let's all right,
thought you
go
were
ahead
done
and wrap it
talking.
up, Sean. Let's give him a
I'm
20
done.
second.
I'm done. Go ahead. Go
All
ahead.
right.
Go
Yeah,
ahead,
if you
Brian.
could show your drawing again, where you have the them steps. If you want to fix that, for the audience and me to see, and draw it how it actually is, because them steps are non-existent. What you just showed, I thought, maybe you meant that as like a drastic, all of a sudden slope. Looks like 90 degrees to me though. There's no step downs. There's a change in water level just that represents the would be slope uh, at each
No,
gate. So the water
it's a
will build
change.
up. So it
It's
will
the
be a little bit lower,
change.
but it's not. It shows in the writing from the pad the guy's holding. It's different at each gate, and depends on how they have it flowing. But that's it. It just it represents the slope basically, and the water built up at the
Okay.
time.
What you don't see and he doesn't talk about is the bottom of that canal. The bottom of the canal is the most important thing. Imagine this. This is how it works. In a canal with locks, it is a constant slope that is engineered. There are locks that stop the flow of water. In a canal that doesn't have locks, because I didn't say it had locks. In a canal that has locks, what they do is they engineer it in sections. If you will, you can imagine each section being its own box. So it's not a slope, it is a box. Each gate allows a certain amount of water to rise in that box to a certain level. Once that box is raised to a certain level, water flows into the next box. There's a solid difference between how things are made, Brian. You need to understand that first.
Yeah, I agree,
Because of
Sean.
that
But
box, and because of that box not being a flat box on Earth, being engineered for flow, that box is not squared. That
okay,
box at the
Sean, let me,
bottom of the
let me
slope.
explain something to you, man, real quick. Okay, the locks. The reason locks are built in canals, like in the UK mainly, and well, all over the world, are to reach bodies of water, like usually large bodies of water that are not tied in to the ocean. Okay, because if they were tied into the ocean, then it wouldn't matter. And if they took down the locks, then the lake would drain into the fucking ocean, bro. The aqueduct is not built like the lock system, bro. That's to reach bodies of water inland at higher elevations, usually very large lakes and such.
Yeah, exactly. That's what the fucking pump houses are for, Brian. You're not explaining anything I don't understand. You're just trying to act like I don't understand what I'm saying.
I think you're projecting a little, man. The way you described it,
No,
I thought you were, if you drew locks, bro, is what I'm saying. You know what it looked like to me.
no, no. Okay. The reason I drew it like this, Brian, is because the main things I wanted to illustrate is that solid line, which would be Earth curvature, and the dotted line that would be the top of that berm. That's what I drew the picture for. That's what I even talked about. I didn't talk about the steps, not once. The reason I didn't talk
Yeah,
about
well,
those steps
but
is
what
because
you did do
all
is
look,
said that
look,
you said the
look,
bottom is
all
important,
again.
bro.
I'm gonna finish.
Hold on, Brian.
I'm gonna finish. Yeah, yeah. I said the
Hold
bottom
on,
of the
Brian.
canal is important. But what I made clear when I drew this picture, when I even told you about this picture, was what was important was that solid line, which I represented as quote unquote Earth curve, right? And then I explained that the reason that the bottom things were like that is if they were accounting for curvature. That's how it would have to be because that's how the boxes are measured. Then I drew the dotted lines. Those dotted lines represent the canal itself.
Okay, well,
So that's what
explain to
that
us
picture was
again.
about.
Okay, explain to us again why the bottom is so important. You just said earlier the the bottom of the canal is very important. Will you explain what the bottom has anything to do with what's going on in there?
I'm doing it right now.
What if it were up and down? Like, what would that affect? Not
That's
much.
exactly what's happening. I'm going to show you right now exactly what happens. That's a very good question, Brian, because that question is exactly why a canal is built the way it is, because it is higher.
You keep calling it a canal, bro. It's an aqueduct. Man,
It's the same thing. It's a canal.
it's also a
Same thing.
man-made structure, but not
Same thing.
quite,
Doesn't
bro.
matter.
It's all concreted, bro, with pump houses. The canals are just dread. They're similar, but it's not the same, man.
Yeah, I know.
Aqueduct.
Boats aren't going through it, so it doesn't have to work the same. Which is why locks. Why I never said locks, but I'm going to show you right now. So on this picture, I don't care which direction you want to go. This is how it works. Okay. See the dark line. The dark line.
Yeah, yeah.
Brian? That just represents, not actual, just represents the the berm, that concrete berm around the top of the aquifer,
All
which
right,
is
show me
still a
where the
canal.
water would be then. If that's the berm, show me where
No,
the
no,
water
nope,
would be
nope,
going.
nope, nope. I only really care where the water is. This all I'm going to
Please,
explain to you right now is
please, please,
how an
all the water.
nope, nope. I'm going to show you how an aquifer works. So an aquifer works this way. Because it changes elevations, because it has to go through different terrains, is they build each section like this, a box. See the box right there? See this box? That's the first box. The pump houses keep each individual box at the same level. And it makes it so that water can be flowing controlled. Now, those gates you keep talking about, those gates are actually underwater about halfway into these boxes. Let me show you where.
The gates are underwater, but the gates go from the bottom to the top, bro. And the channel in the gate
Now, go back to it, Steven.
represents the
Hang on,
water.
I'm gonna show you. I'm showing you. I'm showing you right now. I'm gonna show you. Remember you asked about the water? Let me show you. See the line between those boxes? That's exactly how water is pumped through an aquifer. The difference is between this. With locks, things travel at the top. with the aquifer, it is pumped through those boxes. That keeps debris out. That keeps flow controlled and everything. This is why the top of the water means nothing, because each one of those boxes, sections of a canal, have controlled flow. If something happens to this last box right here, this one, they can stop water here. They can stop water right there by shutting the gate and not pumping any more water.
Bro, the gate is
And this
almost
works.
the gate.
This works in any direction. Any direction.
Right, but it
The
doesn't matter.
reason,
It's all blocked. It's done. It's blocked, and every gate is just blocked completely. Okay, and then they have the water at this aquifer here. They have the flow at the bottom of the gate, flowing basically under the gate is where they open it, which baffles the brain why they would even do that. But they do have it
wait.
flowing under.
Again, hang on, Brian. Are you explaining to me as if you're correcting me by explaining the exact same thing I just explained? Let me make it clear again.
Okay, yeah.
A canal,
I see that.
a canal, like you're talking about with locks, the whole body of water flows in. When you're talking about the aquifer, see that line in the middle of the box? Those are pumped through. When that guy was measuring, all he was measuring was the levels in one box.
Now, do you see water flow? Okay, do you see when they open the gates, man? You get a little bit of flow in them things. You know, it's not like water comes racing. It's only supposed to be 4 inches of slope. This is continual slope, okay, but it's blocked off every couple miles, okay, and then they let water in and out depending on what they need at that particular spot. You know, to me, they like I said, they have an excess pump house, and I don't think they need that many, but whatever they do. But the thing is, you're explaining the locks, okay? The locks are each one is its own body of water, okay? And with that,
I never said locks.
Hold on, please.
Never said locks. I never said locks.
Well, yeah. Let Brian get like at least a 20-second thing out here.
Yeah, real quick, man. Real quick. The way you're explaining, Sean, the aquifer. Okay, if you took out all them gates, you would just have a constant flow going down to the bottom, basically, until all the water that's up top would just. You have.
Oh, Brian, I think you got too far away from your mic. I can't make out what you're saying right now.
Yeah, go ahead, Sean. Let me fix my mic. Go ahead.
Oh, I think we lost Brian.
Again, you're trying to explain what I'm explaining. The reason you don't see a lot of those gates and a lot of the pump houses because the water level, the gates are low. If you were to take those gates, not locks, gates out, what would end up happening is it would basically have pools of water throughout it and then dry spots because they wouldn't be pumping the water anymore.
Okay, you agree. Okay, to me, this is a giant deflection, dude. Okay, fuck, my mic's messing up. Can you hear me?
We can just barely hear you, yeah.
Okay, well, here's the thing. Okay, so the main point is this, is the gates aren't always open. There's not always water flowing, okay? And what he does is he measures the water while it's stagnant. Okay, then the shit opens, the guy measures it, people measure it sometimes, it's all tracked, okay, at their system's place. But he checks it while it's stagnant, okay, while the water's not moving. And what he gets is instead of a 3 or 4 inch difference from one end to the other, he gets a 14-inch difference from one end to the other. What's your explanation on that? So if he flowed more water, that would just make it even lower, Sean, right?
It would be the engineered area of the aquifer. Again, if you were talking about, we were saying level is level, no matter where you are on Earth, and is a measurable amount. So that means in each section that he measured, that you should see a drop. The problem is, Brian, the box that you're looking in, where he's at, if it's running uphill, you're going to have a bigger gap between water and edge at that one end than the other. I don't understand what you don't get about that. Those boxes aren't flat. The sections aren't flat.
I know that. They're sloping 3 to 4 inches per mile.
In which direction? All directions. You understand that, right? It's not just a constant fall.
No, it ain't
And
all
if it is a
directions, bro.
and listen, and when it is a constant fall, what it happens is they put that thing up on a berm so that they have enough leeway between Earth and it for it to drain to its lowest point, right? To get to its lowest point, so they don't have to use as many pumps as you're talking about. But that aquifer goes in all directions. That's why they have pumps, Brian. That's why measuring it doesn't even make
No, it
sense.
does. Oh my God, Sean. Oh my God, bro. Are
Go
you
ahead.
kidding me? You're telling me that the aquifer is not a steady with a gentle as little slope as they could get by with to get water down to the areas. You're telling me that it flows in every direction?
Yes, there are actually areas where it does flow, have greater elevation change. Yes. A really good example of this is the American River Canal System, aquifer system, I'm sorry, in Southern California that runs through the desert. Um, it's very clear. It has to run over, it runs between two mountain regions. That's where these pump houses are very important.
Sean, that
And where
is the
there aren't the
California
pump
aqueduct,
houses,
bro.
listen. And in between those areas where it's not running in gain, it's not gaining in elevation between sections, it does flow. You've already stated that 3 inches per mile. That's
If
why
you
it's
had
on a
water
berm.
coming
It gives you the
from a
space.
big ass lake, right? If you had water in a big ass lake that's and you wanted to get it in a lower region, that's, let's say it's in the desert area, inland a little bit, okay? What would you do? What could you do to get water from one end to the other? You put in slope, right? And then you could get the water to the lower lying areas, right? They're not pumping it. It ain't uphill boat ways, bro, or downhill boat ways. The markers are there. You see the elevations. He shows a couple of them in the video where it's I think
What
it's
are the
like
pump houses? Hey, what are the okay?
3,033
What
feet.
are
They
the
only
pump
have a
houses
certain amount
for?
to work with, Sean. Sean, they have a
What are the
certain
pump
amount to
houses
pump
for?
water away, bro, to get water to where it's needed.
Okay, in that section, there are
What do you think the
areas
pump
that
houses are
have
for,
less
Sean?
elevation. Hey, I'm not going to do this if you're going to interrupt every fucking time I start talking.
Well, you cut me off, bro, and I answered your question, and then I just wanted to just what do you think the pump houses are for?
Yeah. Okay. Those pump houses are to keep flow and for the extension routes that go off. But there are areas where they do actually have locks. They don't call them locks, but they're like locks that have a big area that pumps things. And because of that, where it gets flow gets slow, they use those pumps to keep it going. It gets to a certain level, they can turn the pumps on, they can turn the pumps off. The water gets high enough, they can turn the pumps off completely. You don't even need to. But the reality of it is this: you said earlier that it was following curvature. It's not following curvature. You know it's not following curvature
What do you
because we know 8 inches per mile.
What are you talking about? It's not following curvature. He shows his through the theodolite that it's designed to match Earth curve. But here's the problem: there is no Earth curve, so what you wind up with is more slope than was intended. That's the
What is
whole
Earth?
point of
What
the
is the
video, bro.
in the globe model? In the globe model, what is the Earth curve, Brian?
In the globe model, level is level. Okay, so on a
In
basketball,
the globe, no, Brian,
if you have
Brian,
an inch of
Brian. In
if you
the
have an inch of
globe,
water
hey,
along the
hey, this
whole
is very
thing,
simple,
let me answer your
Brian.
question, bro. Please, can I please
No,
answer your
no,
All
you
right,
didn't
question?
even
hold
let
on.
me.
Yeah, let's hold on, Sean. Hold on, Brian. Just let's try and finish off this topic, and if we got another one, we can go there, or we can bring it to Q&A. Let's
Yeah,
try and
just
wrap this
let me just say one
one
little
up.
quick
No,
thing
I'm
is
gonna finish. No,
I
no, I'm
hate
gonna
when you ask me a
finish my. I'm
question.
gonna
You've been
finish.
cutting me off this whole
I'm
Hold
time.
going
on.
to
He
finish.
was
No,
actually Sean. He was actually in the middle of saying something right now. Hold on a second. Hold on.
I was
On a
in the middle
globe,
of saying my
okay?
question when he cut me off.
Well, actually, he was.
How do you
I think he
fucking?
was
How do you know?
responding to
How do
your
you know?
question. Yeah.
No, I was in the middle of my question when he started to respond. So how does he know?
You asked me how it works on a globe, and I was trying to respond, and I was going to just tell you on a
Okay. All
basketball.
right. If that's the case, Brian, let him get to the end of his question. Maybe he had a little extra there to.
Yeah, but I wouldn't have no problem with him cutting me off. But every time he cuts me off, it's coming followed by me not understanding something. And I just want to make it crystal clear that I've been in this a long time. I
All right.
understand how
Well,
elevation works on a
okay.
globe.
Right. That's fine. Just let him get to the end. I can't imagine his question is going to be longer than 15 seconds. Go
Yeah,
ahead.
go
Sean.
ahead, man. Go ahead.
Okay. Well, one, there's a difference between elevation and curvature. And two, my question was this: what is the curvature of Earth? You didn't answer the question. You went on a diatribe. The answer would be 8 inches per square mile, like you keep saying over and over again. The reason it doesn't match Earth curvature, like you keep saying over and over again, with your own information, I'm going to show you you're wrong, because you've already stated that the aquifer is it drops at 3 inches per mile, so it does not match Earth curvature. So it does not match the numbers you're trying to magically say are wrong.
I never brought up Earth curvature. I told you Demonstrate is going to do that, act like I don't have an understanding. And I'm trying to explain to you that I'm not talking about Earth curve. I made it crystal clear that on a ball, level is level. It's curving, but it's level. So if you have the same elevation, then you're gonna have the same water height. I was trying to make sure you understood that, and because sometimes you know the way you talk, you might not. So I had to reconfirm that you understand that level is level on a ball. On a ball, curved is level. Okay, 8 inches per mile squared is level. Okay, my differential was that in between the two closed gates, okay, with stagnant water, and there is 3 to 4 inches per mile of slope. That's bare minimum, dude. They had to do this over hundreds of miles. They had a minimum of slope to work with. That's why these aquifers are crucial, man. And what happens though, if they do an earth curve, then every mile they're going to have an extra 8 inches. So they're going to have more slope than was intended, and that's going to reflect with higher water on one side than the 3 to 4 inches that was supposedly built into it.
All right. I think we can move on to Q&A unless there's any other topics you guys wanted to cover. One of the first questions we got from Drink a Kool-Aid is, why did Brian claim the fish tank was flat?
Hang on. Can I ask you a question, Demon Stride, real quick? Just clarifying.
Sure.
Is it me, or in the response they interrupted? Was he not saying that the aquifer matches the curvature of Earth? Isn't that what didn't he say that's what the globe model said?
Yes.
That's what it
Yes,
appeared
he did.
to sound like to me. Yeah.
Okay, perfect. So when I'm sitting here telling you, Brian, that if Earth curve is 8 inches per square mile and the aquifer is 3 inches, then measuring the water level and then adding those numbers up.
Yeah, sorry, I interrupted that time. Go ahead, Sean. Go ahead. Sorry, man.
No, I'm good. We can go back to questions now.
All right. So from Drink a Kool-Aid, why did Brian claim the fish tank was flat?
Well, what I'm referring to is is at first he put a piece of sheet metal to try and represent obstruction, but it didn't work. He couldn't get his laser to bend around it. That's in another video. What he had to do is lower it, and he wound up having to lower it below the rim. So what you see in the fish tank, if you watch the whole video of Mick West, you see a black rim, and it's usually at the bottom of every fish tank. It's for reinforcement where the pressure is the most. And the black rim from end to end is higher than his simulated curvature. Okay, so that curvature is just slightly lower than your line of sight from rim to rim. That's why I call it. I think that's what he was referring to.
Wait.
Right.
So what is obstructing the bottom of the fish tank?
Nothing.
Okay, whatever. Go ahead.
All right. So this one is from Ed Freeze. Question for Sean F. Show me a globe drone following the curve at 33 degrees, one front view, one side view, start to finish, HD video. I'll wait. No drawings. Can you do that, drone boy?
Okay, hang on. I got to turn around so you can see my ass real quick, Ed.
Okay. We have another question for Brian from Rocket Man. He says, why does he always have to be very unorthodox? Why does he always have to use very unorthodox situations to try and prove the flat earth?
I'll be honest, man. I do admit that I do that. I'm trying to think outside the box, and and come from angles that are outside the script. I mean, let's be honest. A lot of us here are veterans, and we've been discussing this same shit. So I try and bring some interesting outlooks, you know, and just outside the damn box, Rocket Man. Just so you know.
All right, this one's from Drink a Kool-Aid. So did Sean's lady kick him out of the house? Is that why he's in the car?
Yes, actually, yes. Yes, she does not want to hear this shit.
She said, "If you don't win this debate, no dinner for you."
Well, I think I have nothing to
I'll
worry about, Brian.
sandbag. I'll sandbag at the end, Sean, so you get dinner, bro. I'll sandbag some of these
I thought you.
Q&As.
Oh, my bad. I was going to thank you for doing that from the beginning, but my bad.
This one is for Sean. How many from Space Shark? How many spliffs do you need after this debate?
4.
4. All right, so that brings him up to number 5 on the spliffometer.
I'm at 3 right now.
And ditto, Sean. I was going to thank you for leaving Flat Earth, bud. I'm just fucking.
Yeah. I can't. The having to go outside of the box to explain things doesn't explain reality.
I like demonstration when it boils down to it, man. When it comes down to it, to me, demonstration's king. If you can word it and make sense of it, that's one thing. If you can demonstrate it, that's better. That's why I always like demonstrations and observations.
Me too. Especially when you can look at them and go, this is real world. This is a drastic exploitation of what we think we see. There's two different. You can't really compare them, though. You can't equate them, is a better way of saying it.
I'll concur.
All right, so I want to let everyone or ask everyone who's watching to go ahead and hit that like button, subscribe, share this with your friends. We have upcoming debate with Sean G steel manning the flat Earth against Witzik Gitsit, who's going to be steel manning the globe. I think we're shooting for next weekend on this one. It should be great. I'd like to thank the guests for coming, Sean G. It was awesome having you. Brian, thanks for coming, man. Could you guys go ahead and pimp your shit for a minute?
Yeah, man. I appreciate you having me too, man. Remember, if you want to see some of my content, if you like outside of the box thinking, you know, I try to leave a little room for margin of error. I try to keep it as honest as possible, you know, in case I'm wrong about shit. But if you like that sort of thing, demonstrations, that's why I named my channel Flat Earth Test. I show gas pressure gradients inside containment. I show, you know, how much thrust, adding fire to propelling gas, just miscellaneous shit, dropping stuff and timing it. If you like to see demonstrations and stuff, man, you like outside the box thinking, check out my channel on YouTube. Thank you.
Awesome. And how about you, Sean?
Yep. Thank you, Demonstrate. Definitely enjoyed it. I'm very, very happy that we weren't muted for the first 5 minutes. I appreciate that. If anybody wants to see the content that I used to do, Sean G is the channel. If you search Sean G Truth Army, makes it a little bit easier to find me. I will be live streaming eventually. I know a lot of you are sick of hearing that, but you know, good things come with weight. And other than that, if you want to find me and you want to argue with me, I'll be over at the MMM server, being Modzilla. Thank you,
Yeah,
Demon.
and Sean, that wasn't too bad, man. I'd look forward to a part 2, you know, and I'll try and bring some more presentation, you know, to cover some more topics. Yeah, that wasn't too bad, man. Thanks again, Demon, and thanks, Sean.
Yeah, absolutely. Thanks for coming, guys. And again, both their links are going to be in the description below. We're looking for weekly debates here. We have also Dissecting Flat Earth Fridays on the other MMM channel. Thanks for watching, guys, and peace out.